So I wanted to ask if you have any questions about what was going on the last time, on the last times. So is everything fine so far? Yes. So we were studying the following phenomenon, that if we have some symmetry in classical field theory, namely we had a transformation phi transforms to some g epsilon phi, one option for this epsilon some number. So if it was a symmetry of original theory, then action of the theory under such symmetry modified by epsilon, which now depends on x, it changes in the following way. So in our case, d2x. So it was usual Noether theorem plus all of epsilon squared. And there was a homomorphic variant of this theorem. So if we have a symmetry with a homomorphic parameter, then action of such a field with a parameter depending on z and z bar will become s of phi plus integral d to x d bar epsilon j plus O of epsilon squared. And I did such computations in some cases to compute explicit formulas for this conserved conserved currents G mu and G and J, which was so in this case if phi was on the equations of motion, in this case we had just a usual conservation of this current, which is d mu J mu equals to 0. But in this case it was much stricter condition that it is d bar j equals to 0. And we saw examples of such homomorphic homomorphic conserved currents in the free boson. There was J of Z, which was I d phi, so it was homomorphic because of equations of motion. There was energy momentum tensor, which are up to some constant, but probably I'll write this constant So at this moment it's not important. So it was also homomorphic, and in principle we can write higher powers, and there will also be homomorphic currents. And now I wanted to say a little bit about the consequences of this for the quantum theory. So all this was for the classical case when phi satisfied equations of motion. But now let us ask, what happens if we substitute something of this kind into the path integral? So uh, we had some definition of what the correlators in our theory are. So, namely, a correlator of some fields of 1 of z1 or n of the n was equal to the integral over d phi e2 minus s of phi or 1 o n. Well, why did I put it to the numerator? I can just write that it is 1 over z, where z partition function is just the same integral without fields. Well, I can write it explicitly. Actually, so there's a definition, and in principle we can try to play here the same games as we played in the classical field theory. And namely, what was the first in that case? The first were some equations of motion which were obtained from arbitrary variations of phi. So let us first see what happens with this object in the quantum field theory. So let us ask what is the analog of equations of motion. So, in that case, we had to consider the arbitrary variations of phi and say that we are looking for the saddle point of extremum of this S. And now we can say it in a different way. Namely, we can say that if we shift phi by some arbitrary delta phi, this integral will not change. So, namely, let us write that integral in d phi plus delta phi or 1 of e2 minus s of phi or 1 of z1, which also depends on this field phi, because it is, for example, value of this field at some point, or some exponent of this field at some point. So in principle, it also depends on phi plus delta phi. Sorry, I forgot to write phi plus delta phi in the action. So we have such integral, and since the delta phi is some shift of the integration variable, it equals to the original integral d phi e to minus s of phi O1 On. And now if we expand this up to the first order in delta phi, so the zeroth order will just cancel because this integral is the same on the left hand side and on the right hand side. And the measure is invariant under the shift by constant. So d of phi plus delta phi is d of phi. We just shifted this field by some constant in each point of the plane. So and so we are left with the contribution from the action and with contributions from this field. So it will be something of this kind. Hmm? But what do you mean by Lagrangian? It's the action on the functional. So yes, it's the integral of phi, and S is a functional of phi. So it is a function, the space of functions on a plane. Something huge. And the example you can keep almost always is this. So it's a free theory. In principle, you can think about some interaction, which will break everything. So in principle, there can be some v of phi. Is it fine? Okay, and here we'll have a product of all k of the k computed in the field phi plus delta phi of the k and delta O k in delta phi of the k. This is for the situation where these fields do not contain derivatives. But in general case, maybe it is just fine. Let us write not this variational derivative, but just a usual derivative. So this product and this equals to the integral without all these delta phi's. Uh, so let us now expand everything and get the following identity that sum from k equals to 1 to n correlator where we have O, O1, then dok over d phi of zk on equals, so which comes from expansion of this product. We take one bracket and say that we should take delta phi from that bracket and term of order 1 from all other brackets. So it's one side. In the other side, we have all fields absolutely the same without any derivatives, but we have this integral which comes from variation of the action. So it will be an integral of delta s over delta phi of x integral delta phi of x d2x times O1 of z1 On of zn. So we have this equality which holds for arbitrary delta phi.
Can you repeat why taking the path integral with the phi plus the variation must be equal to the unperturbed integral?
Because this variation does not depend on phi, it is just some constant shift at all points. So we can think about this integral. So this d phi is more or less a product over all x's in C. Integral d phi of x from minus infinity to plus infinity, and it is the same as integral of in shifted variable in the same limits. Delta phi of x. Is it fine? Something interesting can appear if this shift is itself dependent on the field in some trivial way. In this case, we can have non-trivial Jacobian, which is called anomaly. And it appears when we think about scale transformations almost always, and also if we have fermions, their measure is also defined not in such stupid way. So, so in general situation, we should be careful. Okay, so are there any questions about this formula? Yes, thank you. Okay, so there is this formula, and now let us see what follows from it. So on the right hand side is some functional that depends on delta phi of x in any point of C, because it's integral over the whole plane. And the left hand side depends on delta phi only in some number of points. And looking at this, we can immediately write that this integral, that expression that multiplies delta phi of x equals to something. So if this holds for arbitrary delta phi, then what can we say about this correlator? Mm. Uh, no, I would say that delta phi should be arbitrary. Well, if you want to prove that it is zero in all points except the case, yes, you can choose some functions that are non-zero in very small domain, not contained in this z case, and then consider each z case separately. But what should be the answer? Mm-hmm. Thanks. Okay, and this is called the Schwinger-Dyson equation, one of the possible forms of it. So what does it tell us? It tells that this that equations of motion are kind of also satisfied at the quantum level, but they're satisfied up to this so-called contact terms. So if you insert this equations of motion under the correlator, and they will not be identically zero. They will contain some delta functions at the points where they collide with some other fields. And in principle, such equations are not very useful if you work with some interacting theory. They can be solved only perturbatively. But if it is some free theory, then we can recover something that we already know. For example, we can recover the formula for the two-point function. So, for example, let us say that n equals to 1, and S is that S. So delta is so variation of the action delta S over delta phi of x will be d bar phi. With some sign and with some prefactor which I don't want to recover. So if you substitute it here, we'll and n equals 1 and O1 of the 1 is just phi of z, phi of the 1. So delta S over delta phi is this. So correlate of d bar phi of x with phi of z will equal to what will remain in the right hand side. Hmm? Mm-hmm. Yes. Mm.
In a way, shouldn't there be like some addition value of
Hmm?
1,
Okay.
which is the
Could you say it again?
like there should be also addition value of 1,
Ah,
which is the normalization.
but okay, the definition, expression, yes. So here when I wrote correlators, I divided it by partition function without saying it explicitly, but it's the same everywhere. So, and this equation can be integrated. So we can conclude that j of x and z is with some constant this logarithm of r squared over z minus over x minus z squared. So So almost the same argument which is used in classical mechanics works also in the quantum case, but now it gives not the equations of motion, but the value of a correlator. Okay. So uh, but this is not all. In principle, we can ask what about higher correlators, because in principle we know how to compute the how to compute arbitrary correlatorism in this theory, because we know how to compute this path integral with arbitrary source j. We can just differentiate it enough time. But let us ask what happens if we try to compute them starting from this Schwinger-Dyson equation. So let us substitute. It doesn't make sense to substitute the odd number of fields and the correlator, because this because this action is symmetric under phi 2 minus phi, and all such correlations, all such correlators will vanish. So it makes sense to consider only even numbers. So let us now study n equals to 3. So together with ds in d phi, it will give 4. So, in this case, this Schwinger-Dyson tells us that d bar phi of z, phi of x1, phi of x2, phi of x3. So it will be delta 2 of x minus x1 minus z, phi of x2, phi of x3, plus mm, so as a function of z, this correlator has uh, three singularities when z coincides with x1, with x2, and with x3. And we know how to solve such equations for each of these singularities. It just gives this green function. We can do this again, and not even writing explicitly the value of this green function. We can just say that this correlator of 4 fields, phi of z, phi of x1, phi of x2, phi of x3 equals to phi of x1, phi of z, phi of x2, phi of x3 plus phi of x2, phi of z. And so if you draw this pictorially, it looks like this. In order to compute the correlate of 4 fields, you need to consider all so-called parents of these fields. So So I will just repeat the same expression 3 times. and now we need to connect these fields, group them in pairs in all possible ways. Like this, and like this. So each pairing equals to the correlator. So this phi of x paired with phi of y equals to correlator phi of x phi of y. And this formula is called the Wick theorem. Which appears not only in quantum field theory. It is basically the theorem about Gaussian integrals. So if you open Wikipedia, you will find it, for example, near the computation of some expectation values of normally distributed multidimensional random variables. So, and it can be derived also from that formula for the expectation value of integral of g of x of r of x due to x. So by the way, who remembers the value of this expectation value? Maybe approximately. Yes, but you can write it in a simpler ways so that it is easier to remember. You can write it as g of x v1 half correlator of phi of x phi of y g of y d to x d to y. Let me think about 1/2. Yes, it should be there. So it is easy to remember, and because we know that the first order term of this correlator equals to 0 because the integral is quadratic in phi and it's even in phi, and the second order term is on this correlator integral g of x d to x. Oh, 1/2 integral phi of x g of y phi of y d to y. It is just a square of this integral, but with different integration variables, so that we don't mix them plus everything else. And we just see that this first term is having the same coefficient, and all other terms are recovered from the condition that it is Gaussian integral. And this theorem can be derived in the following way. First of all, to get some non-trivial correlator, we need to have an even number of phi's. Otherwise, it is just zero. But when we have even number of phi's, we start differentiating this exponential, and on each step we have two options. Either differentiate this exponential and get another and get phi times j in the well, not in the numerator, but downstairs. And this should be differentiated once again. Or you can differentiate some of these expressions which are already downstairs. And this precisely produces this combinatorics of pairings of phi. Maybe I don't know. Maybe it is easier to do once and see that it is equivalent than to explain. But maybe, or maybe it's also possible to explain. Because so if you have this correlator, again in the same example, so if you want to compute correlator of phi of z, phi of x1, phi of x2, phi of x3, it will be delta in delta z, delta in delta x1, delta in delta x2, of j. Yes, thank you. X3 of this integral. And actually, it is better to write that this integral consists, so we can say that all this integration domain can be split into the small domains around z, x1, x2, and x3. So and we can write it as the integral over so first let us write quadratic parts. So it's a kind of sum of squares. When this integral goes around a small domain uh, around point z, x1, x2, and x3. Times such integral when domains for x and y are different. Sum over alpha less than beta. So this integral can be drawn schematically like it is something quadratic, or maybe maybe the picture will not help much. So we have such term, and we also have some part of this exponential where both integrals go over the domain when x and y are not in this domain that contains z, x1, x2, and x3. So now the question is how to differentiate on this. Basically, it's not even about differentiation. It is about series expansion, because all this should be computed at j equals to 0. So to get a non-zero, we need to consider all possible terms that contain j of z once, j of x1 once, j of x2, and j of x3. But if you look at this term, then they also enter as squares, because here the integrals are all over the same domains, so this will be proportional to j of x squared. So the only relevant term is this one. So we have sum over alpha less than beta, and we have we have all possible pairs of j of x and j of y, and we need to find this. We need to find such combination that contain this, 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 and this only once. So, and such combinations are namely. So let me write again. So one combination is when this integral is around omega z. This integral is around omega x 1. So it's one term. and its counterpart will be the same integral over another two variables. So, and another three terms of the same kind. So if you differentiate this this rational derivatives, we'll have the same formula. So I will not write it again, but it will be a combination of this pairings plus this pairing plus this pairing. And this is how all combinations in the free theory, in sense in theory with quadratic action look like. So, are there any questions about this?
Formally it's the same. I know you can just
Hmm?
definition of the correlator of finance and Taiwan.
No. If you add some potential here, then problems start immediately. Because, for example, here, on this Schwinger-Dyson equation allowed us to decrease the number of fields under the correlator. Like we had two fields on the left and mm, uh, zero field on the right. But in the general situation, we will have two fields. We'll have two fields on the left because of the quadratic term in the action, but we also have a term with the potential, which will produce, for example, phi cubed times all other phi's. So it adds the new field, and you don't get a closed system of equations.
But I was talking about the statement of weak theorem.
Hmm?
So you have a different definition of the correlator of P, which is not anymore like logarithm of R squared divided by absolute value of x minus z. But like the correlator of phi x and phi y is still delta and delta j of e to the aggregation value of e to the jx on x, right?
No, you don't have this formula anymore if the integral is not Gaussian.
Oh, so it has to be a quadratic potential.
Yes.
So my master base.
Hmm?
A master
Yes, it's the only possible option which we can add. So, hmm. Oh, we can add more fields, but the action should still be quadratic. Otherwise, it just does not work. It cannot work because in general situation we don't know how to compute integrals different from quadratic, and the only thing people do, almost the only thing is to expand the integrals in a series and in this nonlinearities. This will be a QFT perturbation theory, Feynman diagrams, and so on. So, are there any questions? But I showed it not only to demonstrate how this Schwinger-Dyson equation can work, but also because we will need such rules if you want to compute something for the free boson. And we will actually compute some other correlators, different from the correlator of two fields or correlator of several exponents. So, do you have any questions? Okay, let me I now uh, talk about the different phenomenon which I also saw in the classical mechanics. So I first decided to perform arbitrary shift of phi, and the result of this was this Schwinger-Dyson equation. But we also know what happens if we perform some special shift of phi, which comes from symmetries of this theory. And let us try to do this with the same action. Suppose that it has some symmetries and try to perform this shift in the path integral. And what we get in that will be called word identities. Okay, probably I can erase this. So let us look at the formula like this, and or maybe on this formula, and rewrite it for the special variation of the action. So, namely, and let us choose this variation of the action in the following way. Let us say that G oh I think let's say that there are some points where we insert our fields O1 to On. And let us say that, so let us call this small domains di, and say that epsilon of x is a constant when this x is I in di's. So that I will not break the symmetry inside this small domains around the insertions. And let us write what we get here. So here we will have on the left hand side.
Does it have to be the same function?
No, not necessarily. Let us write it on epsilon I. So since it is a symmetry, and this symmetry acts somehow on all other fields. For example, if it was exponential, then it will be multiplied by some exponential of the parameter of this transformation. If it was something complicated, it will be transformed in a little bit more complicated way, but in general, it looks like this. So there will be some transformation of this parameter epsilon k acting on a field OK of the k. It's on the left hand side. And this is what we have instead of just derivative in phi. And in the right hand side, we will have the integral so we'll have the integral for d2x let me think what should be the correct way to write this integral. Okay, so we see this expression. So epsilon in this domain is constant, and so it is integral over C, which is actually the integral over C minus all these di's, because it vanishes in there. We can write that it is the integral of C minus union of all di's. So and now if we have something like this, uh, uh, we see that expression on the left hand side depends only uh, depends only on epsilons inside this domains. Uh, and so it does not depend on epsilons uh, in the whole other complex plane. Maybe it was better just to integrate this integral by parts at the very beginning. Yes, maybe let me do this. Maybe let us do such transformation immediately. But otherwise, it is very complicated to think. And by the way, no, the signs are correct. So now let us compare on the left hand side and the right hand side. Right hand side depends on epsilon in all points. And in all points here, but left hand side does not depend on them. And, and the result of this comparison is that d mu, j mu of x equals to 0 when x is not in C minus a union of this small vicinities. So in the first consequence of this equality. So you see the similar phenomenon to the Schwinger-Dyson equation, something that was satisfied at the classical level is now satisfied under the correlators, but away from insertion of external fields. And so, are there any questions about this?
If we integrate by parts after we cut we remove all the disks, you obtain K boundary terms, right?
But instead of well, we can move a little bit inside these domains, so that let me think. Originally, these integrals were just 0. The mm, I would say that at this level we don't have any preference about how to write this integral, because it was some classical computation in a sense. It is just an integral of total derivative, and we don't care even if this integral contains some. So if this integral under the correlator contains some delta functions, it is still an integral of some derivative, and it will be 0. Hmm? No, but also at the quantum level, because if you integrate derivative of the delta function, it will be 0. Because here it was our choice how to write this term in the action. We used this integration by parts multiple times when computed this transformation properties of S. So just our choice to write everything as the epsilon times something. We could equivalently integrate everything to this current J and say that it is minus epsilon d mu J mu. But here it is convenient to write it in this form.
So there's a choice involved.
Hmm? Yes, we can choose the integral which is more convenient. Hmm. Is it fine or not? Okay, so we know this, that d mu J mu is 0 outside this point. But to know what precisely happens around the point itself, we can just put all epsilons equal to 0, or maybe we can just compare coefficients in front of these different epsilons. Uh, and we find that correlator of d mu minus correlator d mu J mu or 1 or n. Oh, how to write it better? Uh, Maybe let us say like this. D mu J mu of x O when x is close to the I, it will behave like a delta function of x minus the I times O1 g epsilon I maybe epsilon I, OI, and if we look at this and I integrate around this small ball around OI, we'll have the following formula. Oh, it. So, what is the meaning of this formula? It tells us that if you take a correlator, uh, if you take correlator of n fields, of an arbitrary fields, and insert here the integral of J mu, which is a kind of, I don't know how to call it, a kind of topological defect. It's insertion of this integral under the correlator. This is integral of J. Then on this correlator will equal to the same correlator, but in which this field is modified by symmetry generator. So if we, so in the multi-dimensional case, it will look similar, but dimensions of this integration contours will be different. In that case, current, conserved current will be in -1 form, and we will be able to integrate it over n-1 sphere around the point. And there will be again this equality that if we insert conserved current and integrate it around some field, this field will be transformed with the symmetry generator that corresponds to this current. And this story has generalizations because here we had fields which were points inserted under the correlators, and symmetries which were this n minus one surfaces. So in principle, it's possible that observables are one-dimensional and symmetries are n minus two forms which can be integrated around this one-dimensional observables or more general things. But and they are called high symmetries. But in this case, it is just this simple statement. Are there any questions about it? Is it fine or not?
Here we are neglecting all the other terms that
We can.
Contribution, the maximum contribution, biggest contribution comes from the delta function.
We can just no. We know that the other terms are zero because the mu j mu is zero everywhere except this small vicinity, and we can also put all these epsilons to zero, all except one. So, and if we just look at this integral around all points, it will be the sum of the delta functions. So. And you see here we see some equality which works under any correlator. So we can write it on some other blackboard. Let me write it here. So equality is that if we integrate conserved current around field at point x, it will equal to g hat corresponding to this current acting on this field. So, and here the picture can be either this, or in higher dimensions that will be something like this. Here it's S1, here it will be S2. Well, the point in this, this equality holds under the correlators. And let us actually try to see such an example in the case of free theory. So So in this case, j equals to, so let me think. So in this case, there is j z, which is d phi. And there is j z bar, which is d bar phi. And if you integrate two of them, then let's say integral of j will be equal to integral dz and d phi plus integral dz bar and d bar phi. And
So if I satisfy the integration of
hmm? uh, mm, mm, no, maybe. Wait. So also good question. Who is the current? Who is the topologic current? Because what I wrote now is definitely the topologic current, because it is zero even without equations of motion. So non-topologic current should have this form. Now let us imagine that we are computing the correlator with with this insertion d z and d phi of z minus d z bar d bar phi of z bar. And here we have phi of x1, phi of x2, phi of x, sorry. And this integral goes around this integral goes around x1. So we will have as before three terms with pairings between this phi and x1. Let me write these terms schematically. Maybe better not schematically. So first question is what is the correlate of dphi with phi of x1? So we had logarithm and we differentiated in the first argument. So it will be 1 over, it will be minus 1 over z minus x1 and for the second integral it will be for dz over dz bar of z bar minus x1 bar. Phi of x2, phi of x3. So I wrote a pairing of this fields with phi of x1 and the pairing of these two fields. And plus, and this integral goes around x1. Plus the same integral around x2. Here we will have phi of x1, phi of x3, plus the same integral around x3. So now the question, what will be the value of that two integrals? Yes, because x2 and x3 are not inside the contour. So these two are 0. And what is the value of this integral? Well, there are two integrals, holomorphic and anti-holomorphic. So in principle, it will be minus 4 pi I. But all these coefficients can be adjusted by a normalization of currents. Phi of x2, phi of x3. So, so we see this effect in the case of correlator with just four fields. There was a symmetry which corresponds to shifts of phi by constant. Phi goes phi plus c. So this symmetry acting on phi is just 1. It does not produce anything. It reflects the fact that it is just a constant shift. So it means that if we act with this symmetry on a field under the correlator, we will just kill it, replace with 1. And this is precisely what happens here. So it does not matter how many other fields we insert, but this integral, if it is computed around some particular field at point x1, just kills it and produces some number. So there is this very stupid example, and a less stupid example is if we take an exponential field, because in that case this will be not one but exponential times e to I alpha c.
I have a
But,
question. So we started with the contour integral around x1.
yes.
And then we differentiated the expression value of phi z, phi x1, phi x2, phi x3. Shouldn't we keep having contour integrals under x1, and then the difference is what we obtain at the first factor, like using weak theorem, for example, we get d dz for differentiation of the three terms that we got, right? But always the contour integral over x1. I mean, the result should be the same because it's always.
But what is the question? Derivative of a field is by definition such field that its correlators equal to derivatives of correlators with field without derivative. Is it a question or?
The question is, so we obtain the first line is equal to integral, let's say dz of dz of the correlator of phi z, phi u, so x1 times x3, right?
Mm-hmm.
And then we apply weak theorem, but we should always obtain stuff that is integral over x1 or over something around x1.
But it's yes, it is integral around x1. Sorry. Yes, I wrote something stupid. It's not the integral around x2. It is integral around x1. Yeah, thank you for this question. So it's integral around x1 minus dz over x over z minus x2 plus dz bar over z2 minus x2 bar. And the same integral around x1. Thank you. The same integral around x1, but with minus dz over z minus x3 and so on. So they vanish because point x2 is not in this contour of integration around x1. So sorry for the mistake. So other questions about this? And you see here that it's absolutely the same. What are the number of all other fields? We could insert here 100 of files in different points, and it would work absolutely in the same way. All that contributions would vanish, and we'll have just one contribution which removes one field at x1. So it means that this equality is satisfied at the level of operators.
About
Hmm? Which?
The integral of the mass of J, right? So it should be not just integral of J equals the integral of dz times the pi minus above.
Yes.
What's,
Uh,
I mean, we should take the integral of star J. We don't have.
But yes, but the question is who precisely is this star J, and how star acts. So well, depends on what we call J, one form or n minus one form, which are both n minus one forms in this case. Oh, let us look at the star in this case. So, mm, um, so it acts on the. Uh, mm, so there is omega, which is mm, I forgot precisely, but 1 over 2i probably dz wedge dz dz bar. I over 2 probably. Yes, and there is j, which is 1/2 dz bar plus dz bar tensor dz. So to compute star, we need g of so we want to take some j, which is some vector a, which is some one form a, which is az dz plus az bar dz bar, and compute a star of this one form. Uh, J inverse of this one form will be 2 az dz bar plus 2 az bar dz. Now if we substitute into omega on the first place, then it will be I over 2 a z bar dz bar minus I over 2 az dz. Without over 2, simply minus I. So the answer is it is minus I az dz plus a z bar dz bar. Thank you. Yes.
That's where the minus sign comes from. Well,
Yes, because in principle we have two alternatives, J or J star. but we know that one of these currents is topological. So it vanishes just because the mixed derivatives coincide. So it's a statement that d squared equals to 0. And if you write something like this, then it means that it's definitely not our current, and we need to take another one with star. So of course it can be obtained carefully, rigorously, but I prefer just to guess on the correct expression. So if you insert here topological current, then its integral with everything will be 0, because it will be integral like dz over z minus x plus dz bar over z bar minus x. So one has pole with residue 1, another with residue minus 1. So any questions about this? So, such formulas like this are called word identities. So, namely, a statement that some of this some of these delta functions equals to the square letters de Moivre is called word identity. So maybe I can write it somewhere. Like this. But now let us remember that we had not only symmetric transformations with constant parameter, we also had transformations with homomorphic parameter. And actually, it's for 5 minutes before the end. Probably I will not start the new topic. I'll just give some announcement of what we are going to do the next time. So, so in this case, the idea will be that we again should study the same disks around the um, insertions of fields, and so call them DIs. But in this case, we will choose epsilon in such a way that epsilon of z bar will be homomorphic in di's. So and in this case, we'll be able to write the formula of the similar kind. Mm. So it will be the sum. So here again, we can say that since epsilon is arbitrary outside the DIs, then this d bar j equals to 0 in this domain. And inside the DIs, we can write the formula of this kind. So so it will be operator relation of OK of zk. And now, since epsilon is homomorphic around this around this point k in the domain decay. We have chosen it in such a way. We can write this expression like this, because the bar of epsilon is 0. And after this, we can compute this integral as an integral over the domain of over the boundary of decay. So it will be up to some factor and the integral dz epsilon of of x, g of x, or k of zk. But it's the announcement of what I will tell the next time. So the main message here is that this formula for transformation of a field by current J will be modified. It will be modified by multiplication by arbitrary holomorphic function that parameterize corresponding transformation. So and it is a feature of two dimensions. First, that we have many such transformations, and second, that this word identity in this case can be integrated. So it's actually similar to a statement that in two dimensions we have homomorphic currents instead of just conserved. So in this, because they can have just a single component. So here we see the same. Since this current has just one component, then we can kind of integrate the bar of J to have just current itself and not its derivatives. But it's some announcement, and when you see the formulas like this, and you know some transformation properties of this field, it becomes explicitly some formula from the complex analysis that some contour integral of some homomorphic function times some other function equals to some value of a function at some point, or some derivative of this function at the point. So it will be some residue computation that comes from conformal field theory. So, is it fine? So you can look, for example, what happened in this free boson theory. Like try to substitute some coordinate dependent epsilon, and try to compute such an integral with all this field given by just phi or by derivative of phi. So you can try to perform such kind of computation, but now with coordinate dependent transformation and with some field which will transform non-trivially. Because, for example, if you take derivative of phi, it will be shifted by by a derivative of this function, which appears in the shift. And it should be visible at the level of this correlators, at the level of such computations. Okay, maybe that's all for today. Thanks for your attention.